Hey, welcome! Today, we're going to talk about one of the absolute biggest ideas in all of calculus. We're going to figure out how to find change, not over a long time, but in a single, precise instant. So yeah, let's just dive right in.
All right, think about it like this. If you drive, say, 120 miles in 2 hours, your average speed is 60 miles per hour, right? That's just algebra. But when you look down at your speedometer and it says 75, that's not an average. That's your speed right now, in this very instant. How on earth do we measure that?
You see, the whole trick is moving from an average to an instant. Back in algebra, we got really good at finding the slope of a line that cuts through a curve at two different points. But to get the speed at one moment, we need the slope at one single point. And that, my friends, is a whole new kind of challenge. So how do we pull this off? Well, here's the brilliant core idea. We're still going to use 2 points, but we're going to imagine them so ridiculously, unbelievably close together that the distance between them is infinitesimally small. We'll give that tiny horizontal distance a name, delta x. And this idea leads us straight to our main tool for this whole adventure, the difference quotient. Now, I know it looks a little intimidating, but trust me, it's just our old friend rise over run in a new costume. We say it like this: f of a plus delta x minus f of a, all over delta x. This formula right here is our treasure map for finding the slope at that single point, a.
Okay, but here's the million-dollar question. If that tiny distance, delta x, is for all practical purposes 0, what happens to our fraction? Well, the bottom, the denominator, becomes 0. And the top? Well, f of a plus a teeny tiny bit is pretty much just f of a, so the top becomes 0 too. We land on 0 divided by 0. And let me be clear, this is not an answer. It's better to think of it like two giants in a cosmic tug-of-war. The numerator is pulling the fraction towards 0, but the denominator, by getting so small, is trying to pull it towards infinity. So who wins? 0 over 0 is really a question, and the answer is hidden in the details. Details we can figure out with a bit of algebra.
And here's exactly how we do it. It turns out there's this super reliable 4-step pattern that uses algebra you already know and are good at. Step 1, you expand and simplify the top. Step 2, you factor out a delta x from what's left in the numerator. Step 3, and this is the magic moment, you cancel the delta x from the top and the bottom. And finally, step 4, we take the shadow of what's left. That's just a cool way of asking, since delta x is basically 0, what real number is our expression infinitely close to? In reality, it's as easy as just plugging in 0 for any delta x that's still around. All right, enough talk. Let's actually put this pattern to the test with a function we all know, f of x equals x squared. First, we plug it into our difference quotient formula, and this is what it looks like. Now, let's walk through our 4 steps.
Okay, step 1, we expand that x plus delta x squared part. That gives us x squared plus 2x delta x plus delta x squared. You'll notice the x squared terms just cancel each other out. Nice. Step 2, look closely. Every single term left on top has a delta x in it, so we can factor it out. This is the absolute key to the whole process. And now for the big payoff. Step 3, we cancel that delta x from the numerator and the denominator. Just like that, our whole 0 over 0 problem has vanished. We're left with just 2x plus delta x. And for the final step, step 4, what's the shadow of this? Well, since delta x is infinitesimally small, we basically treat it as 0. So the shadow of the whole thing is simply 2x. And that thing we just found, that 2x, it has a very special name. It's called the derivative function, and we write it as f prime of x, which we say out loud as f prime of x. What is it? It is literally a slope-finding machine. For our original function, x squared, you can give me any x value you want, and the derivative, 2x, will instantly tell me the exact slope of the curve right at that point. How cool is that? And what's really, really cool is that this process is totally repeatable. If we do the exact same 4-step dance for f of x equals x cubed, expand, factor, cancel, shadow, guess what we find? Its derivative, f prime of x, is 3x squared. The pattern just works. It even works for functions that look a bit trickier, like the square root of x. Now, the algebra here is a little more clever. We have to use a cool trick called multiplying by the conjugate, but the fundamental 4-step pattern is exactly the same. And what do we get?
a derivative of 1 over 2 times the square root of x. And notice something important here. This derivative is only defined when x is greater than 0, which, yeah, that makes perfect sense because the original function wasn't even defined for negative numbers to begin with. So this whole derivative thing feels like a superpower. But every superhero has a kryptonite, right? Does it always work? Well, let's think about a function like the absolute value of x. Right at x equals 0, it has this sharp, pointy corner. What would the slope even mean at a point like that? And it turns out you're right to be suspicious. There are 4 main ways a derivative can fail to exist at a certain point. First, the function could just be undefined there, or it could have a gap or a jump. The slope could go crazy and become unlimited, picture a vertical tangent line. Or just like our absolute value example, the slope as you come in from the left is different from the slope as you come in from the right. The shadows don't match, which is what happens at any sharp corner. But let's not get too caught up in the exceptions. Let's focus on the incredible power we've just unlocked. So the main takeaway is this. The derivative function f prime of x is our superpower. It gives us the instantaneous rate of change, the slope, of our original function f of x at every single point where that slope exists. And this little table here really shows you its practical power. The derivative acts like a detective, revealing the secrets of the original function's behavior. If the derivative, f prime, is positive at some point, that tells us our original function, f, is increasing, it's climbing up. If f prime is negative, the original function is decreasing, it's heading downhill. And here's the most exciting clue. When the derivative is exactly 0, the slope is perfectly flat. That's a huge signal that we might be at the very top of a peak or the very bottom of a valley. So what's the big takeaway from all of this? While calculus gives us this amazing new concept of the derivative, the engine that makes it all run is just algebra. It's algebra you're already familiar with. At its heart, it's all about that 4-step pattern: expand, factor, cancel, and shadow. It's a process that you can absolutely 100% master with practice. And this leaves us with a really fascinating question to think about. We just built a machine that can find the slope anywhere on a curve. And we know that at the very top of a hill or the bottom of a valley, that slope has to be 0. So how can we use our new superpower to find the exact coordinates of those maximum and minimum points? Well, that's a story for next time.